We can get started. Okay, welcome everyone to the first of our seminar series, Science by Diverse Scientists, a CalBridge Physics and Astronomy seminar series. I'm David Strubbe, Professor of Physics at UC Merced. Hope everyone is doing well in these kind of unsettled times. We're dealing with COVID, probably most of you in remote or possibly hybrid instruction going on now, and in many parts of the state we're dealing with impacts from wildfires right now. Hopefully it's a nice change of pace to be participating in our seminar here. Since this is our first seminar, I'd like to tell you a little bit about what it is that we're trying to do here. So this is an initiative that came out of meetings we had for the CalBridge program at the beginning of June for the Strike for Black Lives. And we decided that it would be a nice thing to do as part of the CalBridge program to organize this seminar series in which we're trying to highlight scientific contributions from diverse members of the physics and astronomy community. Additionally, showcase what some of the CalBridge alumni are doing. So we'll have as our second speaker in 2 weeks, Katie Rodriguez Wimberly from UC Irvine, who's an astronomy grad student at UC Irvine and a CalBridge alumna. We want to be showcasing in our talks different paths and careers for CalBridge scholars and other physics and astronomy students, and talking about diversity and anti-racism within academia and the scientific community. And finally, also giving an opportunity to participate in seminars for some of the campuses that don't have a physics or astronomy seminar series going on. So we'll be doing this every 2 weeks. You can check on the website and see our list of speakers as we put that together. So we've got a number of speakers who we've got lined up. We're still figuring out exactly the schedule of when they're going to go for the rest of the semester. We'll be doing this throughout this academic year, and we will have all recordings of the talks on the website, and also on the CalBridge YouTube channel. Those of you who might not be familiar with CalBridge, I encourage you to take a look at the website here, calbridge.org, and learn more about it. It's a program that is designed to connect Cal State undergrads with graduate programs at the University of California in physics and astronomy. So I'd like to introduce the committee that has been working on putting this together. So let's make sure that I'm doing this right. Yeah, I can unmute you. Can just introduce ourselves. Alex, you go first, introduce yourself.
So hi, everyone. Thanks so much for coming to our first seminar. I think this is going to be a great series. My name is Alex Miller, and I'm a professor at Sonoma State University. So great to have you all here.
Carol?
Hi, I'm Carol Hood. I'm a faculty member at Cal State San Bernardino and the Associate Director of the CalBridge program.
Sarah?
Hi, I'm Sarah Kohler. I'm also a faculty member at Cal State San Bernardino, and I am very, very excited to see all of you, well, kind of see all of the names of people who are here today, at least.
Very good. And Aaron?
Hi, I'm Aaron Romanowski, Professor of Physics and Astronomy at San Jose State University, co-director of CalBridge North, and it's great to see everyone here today. Looking forward to this talk.
Very good, thanks all. We'll be doing Q&A through the Q&A function you can see here in the webinar. So at the end, we'll I'll unmute people to ask questions. You can also upvote somebody else's question if you like it, so we can see what are the most popular ones. Great, we're up to 53 people who are signed on right now. Okay, that's the intro that I wanted to do. So now let me introduce our first speaker here, which is Professor Gibor Basri from UC Berkeley in the astronomy department. He's a professor emeritus there, and he's also one of the CalBridge mentors. So made him a good fit for being our speaker to kick off this seminar series. Professor Basri got his PhD in 1979 at University of Colorado Boulder, and then he went to be a Chancellor's Postdoc Fellow at UC Berkeley and later joined the faculty there in 1982. We'll be hearing about all of his many accomplishments in research over the years here, which has included doing work with the University of California's Lick Observatory in San Jose and the Keck Observatory in Hawaii, and being a co-investigator on the Kepler mission doing exoplanet explorations. And at UC Berkeley, he also was the founding vice chancellor for equity and inclusion. Actually, I remember as a grad student in physics at Berkeley, seeing him serving pancakes to people once in this role for one of these events. So anyway, looking forward very much to hearing what you have to say today, and thank you for being our first speaker, Professor Basri.
Well, thanks, David, and thanks to the committee, and thanks to CalBridge for being such a great program. I'm going, let's see, I guess, can I share screen now? Looks like it. Okay. All right, looks like that's working. You guys will let me know if something goes wrong, I'm sure. Yeah, I mean, I think these talks should be pretty informal, actually. I know some of you CalBridge scholars, I know some of the faculty members, and as the guinea pig for this series, I figure anything I do is probably okay since there's no precedent involved. So I'm going to try to keep it reasonably informal. I know everybody doesn't have a degree in astrophysics, so some of the stuff I'm going to say is going to be sort of too technical, but I'll try to give you the gist of it, basically. I don't have the time to explain in detail all the various things that I did on the science side. And I don't know exactly how long it'll take, maybe a little over half to 2/3 of the talk. And then I want to pivot to the work that I've been doing all along while being a scientist to help diversify the academy. And I think the point I want to make to all the scholars is you can do both. You can have a great career in science, and it doesn't mean you have to ignore your other passions and things you want to do in life. What it does mean is you have to be pretty good at time management. So one of the things about an academic career is that's a really strong requirement, is that you figure out how to manage your time well, because you're going to have your teaching duties, your mentoring duties, your departmental service, your university service, your science, your proposal writing, your supervising of folks who work for you, your family, and then any community kinds of things that you want to work on as well. You know, the good news is those are probably all things you want to do, and so you're just always having fun. The bad news is there's not enough time to do them all the way you'd like to, so you just have to make compromises. All right, well, I'm going to launch into this. Basically, I want to share a few of the highlights of my research career. There we go. I actually started, and maybe I'll say a little bit about how I got into this. I actually had no particular desire or clue about what it was I wanted to do in astrophysics. I just knew for sure I wanted to do astrophysics. And when I got to graduate school, the first summer I was looking for some kind of a job with somebody, some research project to do, and somebody had an opening. It was in stellar magnetic activity. And we hit it off pretty well. And so I ended up doing my thesis with that person. And the topic kept me interested. And so basically I've done my whole career just because of that random choice my first summer in graduate school. But on the other hand, as you'll see, I've changed topics somewhat during my career. Not so much so that, you completely leave what you're doing before, but enough so that you, have to read a bunch of papers and figure out what about this new subfield, and, it kind of refreshes things and keeps things going. So when I got to Berkeley, I basically, at Colorado, I worked on the sun first, because that's a magnetically active star. And then at that time, it was very exciting. The first ultraviolet satellite that could take spectra had been launched. It was called IUE. And I was, my advisor was one of the people who was organizing it. And so we had an easy time getting data from it. And so I worked on basically ultraviolet diagnostics of magnetic activity on stars while I was in Colorado. When I got to Berkeley, I thought, well, I should broaden out a little bit. And there was another professor here who was working on star formation. And one of the exciting things about my career, I guess, is that at that time we really didn't know much about star formation at all. These days we know quite a bit about it, and it's nice to have been a little part of that. So the problem that I went to work on was there were these stars that were associated with molecular clouds where people thought stars form. They're called T-Tauri stars, from one of the bright examples of them. And they showed emission lines, spectroscopic emission lines, which look a lot like the solar chromosphere, for example. So it was clear there was something hot going on around these actually relatively cool stars. And some people thought maybe that's some kind of accretion signature, and some people thought maybe this is just really strong magnetic activity. And that was the problem that we decided to work on. And this slide is a view graph. You young people have no idea what a view graph is, probably. But we didn't use to have PowerPoint. We used to have these sheets of plastic, and we put pictures on them and wrote on them, and then put them on a projector and showed them to people. And so this is a copy of a view graph from one of my talks in the late 80s, actually. But it shows the essential parts of what my research was part of. So here's a newly forming star. And during the 80s, it became increasingly clear that a lot of these stars had disks around them. So we didn't even know that when I started on this project. And the disk, is heated by the star and emits it in the infrared. So what I have down here, and I hope people can see my cursor. Can somebody nod if you can see my cursor? Yes, okay, great. So this is the wavelength of light, from ultraviolet through visible and infrared and microwave out here, and how bright the thing is here. And basically, T-Tauri stars had this really strange spectral energy distribution. They were very, very broad. If it was just the star, it would have looked like this yellow part here. That's what a young star should look like. But it was clear that there was a lot of ultraviolet light out here, and we could see that with the IUE satellite. And over here, there's also a lot of infrared light. And there were also new satellites and ground-based experiments. Infrared astronomy was sort of just getting going then, that showed that this was true as well. And the interpretation of it, which is the case, was that you're looking at a young star surrounded by a disk, and then there's some kind of very hot, bright process going on that's producing ultraviolet light. And so the explanation was that the disk is still accreting material onto the star. When the material crashes into the star, it generates this bright ultraviolet. And so that this was a sign that the star is actually still in formation. My particular role on this was partly to study the ultraviolet side of things. So using the IUE satellite and optical blue spectra, we studied the spectrum. And so here is a spectrum of one of those T-Tauri stars. And basically, you can model the star itself, and then you see these bright emission lines. Those were the ones that could have been chromospheric. And part of the work I did showed that actually they are. So that was a sign that these stars must have very strong magnetic fields. But as we took higher resolution spectra of them, some of the lines turned out to be very, very broad. and it looked like the velocities there were much higher than you would expect for just the star. And that was a sign that it was due to actual accretion onto the star. And then you see this jump here in this model to explain why the ultraviolet here is so bright. And that is the accretion, accretion shock, basically. So, you know, we did that, and we also started monitoring these stars because they showed variations from night to night, which became less odd when you realized that there was ongoing accretion. The fact that the chromospheric lines were so strong meant that probably the star had a really strong magnetic field, and maybe the disk couldn't actually reach to the star. The accretion took place finally on stellar magnetic field lines. And so this is called magnetospheric accretion. And this is a plot from one of my most cited papers, the one that kind of put all this together. Here, this is time variation. And you can see that the star got brighter and fainter over one rotation phase. And the amount of energy that was involved here was really just too much to be chromospheric. And so we said that this is clear evidence that there's magnetospheric accretion on T-Tauri stars, and the magnetic field is not aligned with the rotation axis. So you see the accretion pole going round and round. So by the end of the 80s, you know, we started this project sort of at the beginning of the 80s. By the end of the 80s, we were pretty sure that that's what we were looking at with T-Tauri stars. Another thing that we did was started monitoring the spectral lines much more carefully. So this weird thing over here is a 3D representation of the H-alpha emission line. This is a bright hydrogen line. The wavelength or velocity goes this way, and time runs this way. So you can see it's changing night to night, basically. The time here is in days, so each tick is a day. So you can see that the star is showing quite strong variability. There's an absorption feature over here in the blue, which we did interpret as the accretion onto the star. And then there was also a wind feature. And because of the variation and the way it behaved with the rotation of the star, we actually were able to confirm a model that was also developed at Berkeley about how this works. So here's the tilted star with its magnetic fields interacting with the disk. The wind comes off the disk here like this, and the accretion goes on to the star like that. And then the thing spins, and both the disk and the magnetic field are not, you know, axisymmetric, and so you get this fun stuff going on. And one of my students spent 40 days and 40 nights at Lick Observatory for his thesis. That's where this data came from. That was one of the drought years in California. So T-Tauri stars are up in the winter, which is not a good time for observing at Lick. But we were lucky that year. It was a drought, and he got almost all 40 nights on this thing, and we made a lot of progress that way. Another fun thing with the T-Tauri stars was looking at binary T-Tauri stars, where it's pretty close binary, and the orbit is eccentric as well. And so the stars are, you know, they come close to each other and go away, and come close and go away. And they're surrounded by a circumbinary disk. And there were these models, I didn't do those, there's a theory basically that said this eccentric situation is gonna basically perturb the disk. Every time the little guy comes out near the disk, it's gonna create an accretion stream, and that's gonna come in, and it'll actually sort of impact the stars when they're close together. And we were able to do these observations here. Again, here's the H-alpha line on different nights. And here is another chromospheric line, the ionized calcium line. And, you know, I'm not going to go through the explanation, but basically this model got confirmed by these kinds of observations. That was important because we also think that this must go on in order to build giant planets. You know, when they form in a disk, they'll open up a gap in the disk, and then you wouldn't be able to get any more material on them unless something like this happens. And accretion streams can still make their way to the forming planet. So we actually this is a stellar example of what probably happens in giant planet formation too. Okay, well, as I said earlier, the underlying theme for my research is stellar magnetic activity, and I did start on the sun, so I just thought I'd throw in this series of solar pictures. Here's what the sun looks like in white light, basically. It's pretty featureless. If you look super closely, you might be able to see some graininess to it. Those are convection cells on the surface of the sun. And the only thing you can see in the invisible is these dark spots, which are places where a strong magnetic field is coming out through the surface of the sun. It's inhibiting the convection. That makes it a little cooler there, which makes it darker. That's these sunspots. And there are these other subtle features, these yellow patches, which are mostly only seen at the limb. And those are called faculae. And they're also signs of magnetic field. But when you go into the ultraviolet, you can see what's going on much more easily. The ultraviolet is more opaque than the visible, so you can't see into the sun as far, so you're seeing higher up in the solar atmosphere. And that's where magnetic fields are really starting to make it hot. So now all the white patches here and the yellow patches are places where the magnetic field is stronger and it's heating the chromosphere. These dark filaments are actually places where the hydrogen is suspended over the solar surface by the magnetic field, and it actually then cools off and makes it dark like this. And if you move over into the X-rays, which of course you have to be in space to see either of these, because our atmosphere absorbs these energies of light. Now you see the solar corona, not as you probably are used to seeing it in an eclipse picture, total solar eclipse. That is actually just white light from the sun reflecting off the electrons in the corona. This is the actual coronal emission, which is, corona is a few million degrees, and so it's all X-rays. And now you can see it's very structured, and that's all magnetic structure, basically. And you know, these are, in modern days, we can do high-resolution X-ray pictures. So now you can really see the beautiful magnetic loops over the sun and the hot, chromosphere below them. And you know, these are on the sun. These are very big features. So here's the loop set, and this is the Earth to scale. I mean, these things are enormous, and sometimes the magnetic field gets twisted into configurations it doesn't like, and basically explodes and tears. And then you get flares on the sun, and also these coronal mass ejections. So all this is a huge amount of hydrogen leaving the sun due to magnetic tearing and flinging out of the coronal mass ejection. I bring it up because this is why people have gotten very interested in stellar magnetic activity again more recently, as I'll explain in a second. But before I get there, another part of my career had to do with, okay, so we're so interested in these magnetic fields, can we actually measure them? Can you directly measure the field on other stars? We can do it on the sun, certainly. Turned out to be, it's a hard problem. The field has very subtle effects on the spectrum of the star, for example. So this is what you expect to happen to basically the residual spectral line. Here's what the spectral line does. If you pick a line that's very magnetically sensitive, and you have fields that are very strong. Remember, the field on the Earth is like 1 Gauss. These are thousands of Gauss. Then the Zeeman effect will actually change the shape of the line. And the more field you have, the more the shape changes. And so if you divide the unmagnetic case with the magnetic cases, you get these changes. And so we were looking for those. And here's the residual division. So that corresponds to this. Here's the actual spectral line and the model with and without magnetic field. And you can see it's a very subtle thing here. And you also need very high spectral resolution. So this is 0.5 angstrom on either side. And you need really good signal to noise as well. So we have to work very hard to do these. But we saw this, this residual signature on some stars, and we were able to interpret it in terms of a field strength and a filling factor. you have to use different lines to sort of pull those two apart a bit. At any rate, this was work that I was doing basically on first solar type stars, other stars, and then later, we were able to develop a method to do it on T-Tauri stars. They're fainter, so you couldn't get spectra like this, at least not at the time. Now with the Keck telescopes, you could work really hard and try to do this, but the other unfortunate thing about T-Tauri stars is they're so active that these spectral lines are kind of messed up by that anyway. So I developed a different technique, and we were able to pull that off on the T-Tauri stars and prove essentially that there really are, multi-thousand Gauss fields on these stars. And so this whole model of the magnetospheric accretion is quite plausible given the fields there. Another way that you measure magnetic fields is indirectly through their effect on heating the outer atmosphere. And so I did a bunch of work on that as well. Here's two stars, Epsilon Eridani and 40 Eridani. They just happen to be in the same constellation. And they're about the same spectral type. But one of them is magnetically inactive. That's this guy, which, the spectra look essentially the same, except around here. This is the core of that ionized calcium line. It's a line that's opaque enough that the core of the line is formed in the actual chromosphere, but the wings of the line are down in the photosphere where the star doesn't really look very different. And you can see that Epsilon Eri has this bright emission feature, and that was one of the stars in the previous set here, Epsilon Eri here, where we could measure that indeed there's a strong field. On the sun, you can look at small regions that are magnetically active or not magnetically active, and you get this same kind of effect. So I did a bunch of work on measuring calcium and other diagnostics like that on other stars. Here is a case where we actually were able to measure the field and measure this is essentially a measure of calcium emission here, and show that they're related the same way they're related on the sun. And the relationship goes up much stronger to much stronger fields and much stronger chromospheric activity. If you can do spectra like this from space, like with the IUE satellite, then you're in much better shape, and you can see chromospheres that are not as strong. And one big thing that I and a whole bunch of other people worked on through those decades is the fact that the rotation of the star is correlated with this magnetic activity and the actual magnetic fields. And we understand that through the dynamo action that produces magnetic fields. One of the things that depends on is the spin of the star. Another factor there is that, yes, that's true, but on the other hand, once you have this strong magnetic activity, you get strong magnetic winds from the star, and those tend to torque the star down. It's not able to swing the field out at great distances like that, and so it starts losing spin. But of course, as it loses spin, the magnetic field is getting smaller. And so there's this whole relationship between age, spin, and field. And now we use it to actually date stars. And that field is called gyrochronology. Okay, well, now I get back to the fun part. Why did this get to be interesting again? Well, this same activity can be deadly for planets. So remember, I started basically I was on the faculty in 1982. The first exoplanet wasn't discovered until 1995. So we didn't know anything about planets up to then. And then once people started discovering planets, of course, the question is, are they habitable? And now we've come to realize that a lot of Earth-sized planets, the ones that we're finding, are around red dwarf stars, where the planet has to be pretty close to the star because the star is so faint. So in order to make it warm enough to be nice, you get to bring it close to the star. But those stars are at least as magnetically active as solar type stars, only now you're putting the planet right up next to them, where there's still all that ultraviolet and X-ray and the flares and the CMEs, only now you're sitting much closer to them. And in fact, there's direct evidence now that planets lose their atmospheres over time if they aren't fully protected by their own magnetic fields, and maybe even then. So that's a current topic of very active research. So I gotta check my time here. I should put my clock where I can see it. Okay. So those red dwarfs, you know, do they have the same kind of magnetic fields as other stars? That was a question because red dwarfs are fully convective. The convection goes all the way to the core, whereas in the sun, it only goes 30% down. And people thought the magnetic dynamo operated on the interface between the convection and radiative zone. So there was a question, you know, well, so, but what if the convection zone goes all the way and there's not that shear layer? Do you get magnetic fields? So that was a topic for me in the early 2000s. Developed yet another way of measuring magnetic fields on M stars using molecular lines. I'm not going to explain that either, but you know, here's a sort of probability diagram on what's the magnetic flux and what's the rotation rate of the star. And we were able to do this for a bunch of stars and got a diagram like this again, which looked like the diagram for example, X-ray activity and rotation on this axis. So stars like the sun are actually quite inactive, so they lie down here. As you spin the star up, the activity goes up until it reaches a threshold, and then it flattens out. That we call this saturation. And so we're able to show that this, in fact, this plot is for red dwarfs, that the same kind of relation held for them as held for solar type stars, and that indeed a lot of red dwarfs have very strong fields. Okay, in the 90s though, I changed topics somewhat, at least for a little while, and I wanted to spend a little time explaining that one. What happened is the University of California developed the technology to make much bigger telescopes. So the biggest telescope to that point was the Palomar 5-meter telescope that Caltech ran. We developed the capability for doing hexagonal, you know, tiled segments of a mirror and making that 10 meters big. But then you have to keep the segments have to stay exactly where they're supposed to be part of a whole mirror. And that was a new technology. It's now, of course, quite common for very large telescopes. Anyway, the first Keck telescope came online in 1993. Caltech had half the time, and UC had the other half of the time, basically. And so all of us astronomers at Caltech and UC said, "Oh, we just have a telescope that's twice as big as anything in the world. What could we do that's pretty significant with that?" And so each of us had our own, you know, ideas and pursued our own research programs. I decided to see if I could discover brown dwarfs. So what are brown dwarfs? Well, they're kind of the missing link between stars and planets. So the most massive planet you can have is 13 Jupiter masses. You go bigger than that, you start getting nuclear fusion in the core, and we don't want to call it a planet anymore. But the smallest stable star, red dwarf, that you can get is about 75 Jupiter masses. And so the question is, what about in between? And no one had been able to find an object that they could prove was in between those two masses. And there was a particular technique that I wanted to try, being a spectroscopist, which was called the lithium test. And here's briefly how it works. Okay, so if you have fusion in the core of the star, you're burning hydrogen to helium. Turns out lithium is a pretty fragile element. It'll burn up too, basically. You'll destroy the lithium in the nuclear burning core. Now, if you have a star like the sun, that could go on in the core and you might never see it at the surface. Depends on how deep the convection zone is. The convection zone mixes material from wherever the bottom of it is up to the surface where we could get a spectrum. So if the lithium burning region gets touched by the convection zone, then you'll see that lithium is being destroyed. For a red dwarf, a low mass star, I said earlier, the convection zone goes all the way to the core. So for sure, you're going to see it there. So if you have a red dwarf star and it starts hydrogen fusion, it will quickly destroy its lithium, and lithium will disappear from the surface because the star is fully mixed. On the other hand, if you have a brown dwarf, it never gets to that hydrogen burning phase. So it doesn't destroy its lithium, but it's also fully convective. So if you still see lithium on the surface, after the amount of time it would take to do this, then you must be looking at a brown dwarf. So that was essentially the test. And unfortunately, the surface appearance of this object and this object are very similar. They're both dim red star-like objects. So you need to take a spectrum and see whether lithium is present. And that was hard. A, you need to know where to look, and B, you needed a big telescope to be able to do it. And so because of the age factor here, we looked at clusters, and in particular, the one you probably most of you know, the Seven Sisters or the Pleiades cluster, was about at the right edge, so that all the stars should have destroyed their lithium, and the only dim red objects left with lithium would be brown dwarfs. And here's the observation that I made. You know, this is what the lithium line looks like. These are two models here, the full lithium and some depleted lithium, and there's the actual spectrum of the first object that showed lithium here. So everything to that point hadn't showed any lithium. So that was exciting. I mean, I think I said here, this was kind of the most exciting and consequential event in my scientific career. You know, when I took the spectrum, it took a while to reduce it and, you know, be sure that wasn't noise and so on. Then I thought, oh, I'm the only person right now on the Earth that knows that that's a brown dwarf. That was not completely true, but it was exciting. It turned out there was another group at Caltech using a different method that kind of got to a brown dwarf around the same time. So can't really quite say that. But the other thing that happened at that same time, basically for the same project, is in order to do the lithium tests, I said you need to know that the stars are old enough to have destroyed lithium, or if they're younger, you would know how low a mass a star would have gotten to this lithium destruction so far. And everybody knew what the age of the Pleiades was. It was 70 million years. And so you could draw a line on the diagram here that would be where lithium burning would have advanced down to after 70 million years. And that line was about here. And in the first time we did this project, we observed these stars here, and they didn't have lithium. And that was weird. It was like, these are faint enough and red enough. They really ought to be brown dwarfs according to the evolutionary model. And yet they've destroyed their lithium, something strange. So then when I found this first one down here, I said, oh, you know, this one doesn't have lithium and this one does. The lithium boundary is right here. But that shouldn't be there. In order for it to be down here, the Pleiades would have to be 120 million years old. And in fact, it turns out this is a good way to date young clusters because the process of saying it was 70 million years depends on what happens way up at the other end of this diagram for high mass stars. They don't have long lives, and they burn their way through their fuel and then they go off the main sequence. And that was how people arrived at 70 million years. But it turns out the process that gets them off there depends on convective overshoot and some other stuff that theorists had sort of swept under the rug, whereas the lithium burning issue was really very straightforward. In fact, a colleague assigned it to his graduate students as a problem set, and one of them actually solved it, and then they wrote a paper which got a lot of citations showing that, you know, yeah, you can work this out almost on the back of an envelope. So that became the lithium dating method, and it's been used to date a lot of young clusters as well. I don't have time to go through this diagram, but this is sort of the net of all that. You can get something about age, and you can see how the lithium depletes. And basically, if your star is in this arena here, it's got to be a brown dwarf, no doubt. Okay, well, that kind of got me onto another fun topic, which was what is a planet? So the reason that came up really was that, you know, Pluto was under attack at that time. In fact, Pluto had kind of been shot by Neil deGrasse Tyson when they opened the Rose Center. He didn't make Pluto a planet, and that was because the Kuiper Belt had been discovered and so on. So people started saying, well, yeah, so what is a planet? And recognized also at the upper end, when do you not have a planet anymore? When do you have a brown dwarf? And how can you tell? And so I got involved in that argument. And I came up with these 4 arenas in which people were talking past each other. So some people, like me, thought you should define planets by their characteristics. Certain mass, doesn't have fusion, is round, things like that. Other people thought, oh, planets really should be orbiting stars, and they should clear their orbit of stuff like this, and we should define it that way. And then a third set, and these are mostly astrophysicists, not the public, said, oh, no, planets, you make planets by crashing lots of small things together until you build up the object. And you make stars by collapsing clouds. And that's so anything that's made by collapsing a cloud is not a planet. Turns out the real situation is quite a bit mixed in all of these. And then the fourth criterion is culture. That is to say, if you make a definition, does anyone believe it or want to use it? And so I wrote an article with Mike Brown, who was in fact the final slayer of Pluto. And we disagreed on Pluto, but there's this very nice article that we wrote about what is a planet, that you can read and see what all the different arguments are. Okay, and then the last topic I wanted to get to was Kepler. I got involved in Kepler again because of my interest in stellar activity. People were worried that, so Kepler was a 1 meter telescope that was going to look for exoplanets by watching for transits. This is an actual picture of a transit of a sun-like star by an Earth-sized planet, namely our sun and Venus. Obviously, Kepler wasn't going to see anything like that. All it could do is monitor the brightness of stars, and if a planet went in front of the star, that would knock the brightness down a bit. But the problem is, those nasty sunspots. They could be quite a bit bigger than planets. Remember, you saw that to scale picture. And people were worried about whether the sunspot signal would just mask the planet signal. And my early role was to say, no, that's not a problem. The sunspot signal is slow. It takes place over days. And the transit signal is hours. It's fast. And we'll be able to tell the difference. So here are some Kepler light curves. These do not show planets. The ups and downs here are in fact star spots on these stars, and the star is rotating. And so you're seeing more spots and less spots, more spots and less spots. And basically for the last decade or so, this is what I've been concentrating on. Looks very information rich. We should be able to learn all kinds of things about stellar activity and differential rotation on stars and stellar rotation periods. It turns out it's a lot trickier than it looks. I'll just say that. This is just one result that we got that was clear. So this is basically how much amplitude is in these light curves. That's on the vertical axis, and then the temperature of the star on the horizontal axis. And the sun is right in here basically. And most of the stars Kepler looked at are here. This is as big an amplitude as the sun can muster. And so there's a lot of stars up here that are more variable than the sun ever would be, but it is still star spots. So those are more active stars. You also can see that cooler stars are more variable than solar type stars. And then we do models to try to explain these light curves. And we put spots on with various sizes, and we let them rotate at different periods if we want to do differential rotation. And I just finished a big paper saying, I don't think we have been knowing what we're doing very well. Most of the results over the last decade have this major problem with them. But I'm not going to say what it is, but it's been another interesting effort, and there continue to be photometric missions, and we really would like to get stellar information out of them as well as planets. And so this is going to be a continuing project. All right, that's it for my astrophysics. I want to take the remaining time to talk about diversity efforts. And I've concentrated primarily on faculty diversity efforts. So that's mostly what I'll talk about, although I've always been involved in student diversity efforts as well. And the thing is, you know, if you want the institutions to change, you have to get at their policies and their practices. You know, you can get everybody to get excited about, oh yeah, we really ought to have a more diverse faculty, but how are you going to get there? And what is it about the way the institution operates that's in the way of that, basically? So I'm just going to give you a sort of a flavor for the kinds of things I've worked on, some of which I did as Vice Chancellor, but a good part of it was done before that. And I'll say a little bit about how I got involved and, you know, what that might look like. So here are some of the, you know, the arenas in which one works on this topic. One is, you know, strategic planning. I actually came on this call. I had to get off of a call that the astronomy department was holding as a Zoom session on our latest strategic plan in our department for these issues. So it's an ongoing effort, and you know, it happens at the whole system level. We have both the CSU and the UC systems, at the campus level, at the division level, like the Division of Mathematical and Physical Sciences here at Berkeley, and at the department level. And making a plan isn't enough. There has to be built-in follow through, otherwise it just sits on a shelf. Then, you know, for faculty, and actually this would look like admissions for students, you know, what's the process? What kind of oversight does it have? What kind of quality control? You know, is there any incentive to diversify? And then what's the transparency of it? So all these things, we know when you delve into them, there's a lot of stuff under the rug that you have to get at, and then you have to get someone to change it, basically. Another arena is reward systems. So people who work on these things, are they penalized for not doing their research, or are they rewarded for, you know, moving the institution forward? That was one area that I did make some progress in. And again, well, actually that could be systemic, departmental, or campus. On the other side of that, review systems. So in particular, all departments undergo a periodic academic program review. And until, you know, sort of the middle aughts, that had nothing to do with diversity, basically. So if you don't put it into the review process, people don't have much of an incentive to worry about it much. You know, so again, all the aspects of that. And then, you know, I talked about transparency a minute ago, but is everybody aware of what progress is or isn't being made? How accessible is the data? And is somebody putting it up on the web? And, you know, is it easy to find? And what does it say? So this has always been, for me, an effective tool, what I call data-driven advocacy. You put the data in front of people, they can argue about whether it's valid or not. Great, make sure it's valid. And then after that, they're like, well, yeah, okay, that is what the data says. Yeah, maybe we should do something about it. But finally, there's leadership. And you really, the people at the top have to be on board. If they're not on board, anyone who doesn't want to get on board won't get on board. So that's very important. I'm not going to go through this, but this was one of the accomplishments, actually, before I was Vice Chancellor. You will now know this as regental policy. Actually, the regents, you know, were the ones who started the whole Prop 209 thing in the sort of mid-late 90s. So they were bad actors at that point. But as we got into the 2000s, there were changes in who was on the Board of Regents, and we managed to get this regental policy in place. And frankly, I wrote a bunch of this, but it was done through the academic senate first. So every campus has an academic senate. That's the faculty body, basically. Then there's a system-wide academic senate, which is where this had to come from. Getting the Getting all the UC campuses to sign on to this took about 2 or 3 years and a lot of changes. And then it was endorsed by the chancellors, all the chancellors, and then it was endorsed by the president of the system. And at that point, the regents were like on board too. I just note the last words here. University particularly acknowledges the acute need to remove barriers to the recruitment, retention, and advancement of talented students, faculty, and staff from historically excluded populations who are currently underrepresented. That's the bottom line as far as I'm concerned about DEI work. Well, there's climate as well. And here's an example of data-driven advocacy that we used at the time. So this is the Berkeley faculty headcount by race and ethnicity. Underrepresented minorities, that is Black, Latino, and Native American, and Asian American. And you know, when affirmative action came in, before that there was essentially nobody present. And here it was steadily increasing. You know, here's where I joined the faculty. And then it leveled off. It was hard to know why exactly. And through the 90s, you know, Prop 209 came in here. That didn't really have an effect either. There was a recession here and another one here. This seemed pretty impervious to anything. And I said, as a physicist, I have to ask myself, you know, what's the driving force behind this equilibrium? And how are we going to get it to move? You know, it ain't moving. And by the time that resolution was passed, you know, it'd been 15 years flat like that. And that was true for the other UC campuses as well. So that's where the data-driven advocacy came in. When I was vice chancellor, we started doing climate surveys as well. And here's just one example. So we did a campus-wide survey. We did 2 of them. And then I actually was co-chair of the system-wide survey. So then 450,000 people in the UC system took this climate survey. And here's just one piece that was kind of important. Basically, each population was asked, what do you think the other populations are going to say about the climate in this place? And each population, for the Chicano, the Asian, the white population, and so on, what do you guess the other populations are going to say about how satisfied they are with the climate? It's basically, how would you rate the climate for persons of this background? And what happened was the white and Asian populations thought the African American, Latino, and Native populations were going to guess, you know, they weren't going to be as happy as them, but they were about 30 points off. The populations were about 30 points lower than they expected. And that kind of got everybody to wake up and say, oh, wow, yeah, I guess I haven't really been in touch with this. And that helped move things along. Another thing, as I said before, is academic program review. And so the campus made a strategic plan in the early 2000s, and we were able to get words into it about like this, you know. When you review a program, does this program engage students and faculty from the full talent pool? These are little code words that everybody was comfortable with. You know, we're looking for really talented people. Are we looking everywhere for really talented people, or only in certain populations? You didn't have to argue about racism directly when you used those words. You know, now maybe people are a little more woke and you can go there, but this is kind of how we came at it then. Once these words were in the campus's strategic plan, you know, the next year when the first reviews came through and I was on the committee that was looking at them for the Academic Senate, I said, oh, I thought we cared about that now. I don't see it in these reviews. And then they said, oh, that's right, yeah. Somebody should write, you know, guidelines for the review process so that you do see it next time. So fine, we'll be happy to do that. And so that was sort of how the process went. And these are some of the things that are now in place. So for example, the diversity committee is now one of the committees that sits on the review board. The campus automatically compiles the diversity statistics for departments. They don't have to do it themselves. They can't forget either. The external review committee gets asked a whole bunch of questions. How do you think the department does on this and this and this? Oh, and here's all the data you need. The department has to have a plan on how it's going to do better, and then it has to explain how well that's working. And then finally, and this really comes down to the provost, who is the person who oversees who gets faculty allocations in the future, and you need to pull all that in there as well. Another thing I did as Vice Chancellor was I created this faculty equity advisor network. So every department has to have a tenured professor who's the faculty equity advisor. They have to meet with the Division of Equity and Inclusion a few times a year. Information flows in both directions there. We can see how things are going, and we can help with, here's new techniques, or here's something that worked, or here's something that didn't work. And then after a while, we were able to actually build them into the search process. So they have to actually sign off on the department's search plan, or it doesn't go forward. And then when the applicant pool is almost closed, they have to sign off that it's sufficiently diverse, or it needs to stay open. And so that's helpful. And then, this kind of work also needs to be compensated. And so I didn't mention, but at the system-wide level, into the faculty academic personnel manual, we got explicit language that if people are doing this kind of work, that is noteworthy and worthy of reward and credit. So that's now part of the system. Oh, I guess I did have it here. So that, this is in the academic personnel manual of the system, UC system, and it says, because we have the region policy that says diversity is important, work that advances that is also important and must be taken account of in promotion and tenure and so on. Actually, this has gotten enough traction at Berkeley that most faculty now feel like they need to put something there. So they look around for some kind of work they can do, so they too can tout their work in this area. Some of it's worthwhile, some of it isn't, but it's nice that everybody thinks that it's worthwhile. And I think I talked some about some of the things we changed in the faculty search process, so I won't dwell on that because I'm running out of time. I'm going to go right to here. So here's that same data graph, but now up to 2018. And this is when we really started getting things in place, when that strategic plan and so on. And yeah, actually had an effect. I stepped down as Vice Chancellor here. And the last thing I did was I took this graph and I said, we like to do numerical modeling in astrophysics. Let me put in all the factors that I think are operating here and project forward into the future. And we did a model of the faculty diversity at Berkeley in the future, and we showed that by 2050 we would actually achieve parity with the current availability pools for women and underrepresented minorities. And I said, well, so anybody want to argue about this model? And if not, is 2050 fast enough, really? And that was another example of data-driven efficacy. So I think that's about all I had to say, yes. I will stop there and take questions on astrophysics or diversity or whatever. Thanks for listening.
Sorry, unmute myself. Thank you very much. We've got a couple of questions in here, and anybody else who has questions, please feel free to write them into the Q&A. So we can go first to Gwen. Let's see if I remember how to do this. I think I can unmute you, Gwen, and then you can ask your question. Maybe Gwen isn't here anymore. Okay, well, I'll just read the question. Gwen Henley asked, will it ever be possible to directly measure exoplanetary magnetic fields using spectroscopy?
Before we do that, we hope I mean, there are experiments now that could indirectly detect the magnetic field on an exoplanet through its interaction with the stellar magnetic material. So the aurora, for example, on the Earth is partly due to the Earth's magnetic field and partly due to the solar wind, which is due to the sun's magnetic field. And if you took, I mean, Jupiter has pretty strong aurorae, and if you took Jupiter and moved it, to a 10-day orbit, those aurorae would be a whole lot stronger. And so you should be able to see them in radio emission. And there are ongoing experiments to try to see that. Sadly, no one has actually seen it yet. To actually get a spectrum of the planet that would show, say, Zeeman broadening, no, that's not going to happen anytime soon. But that doesn't mean we can't, make some progress on, do these planets have magnetic fields?
Cool. Okay. Next, let's go to Wing. So you go ahead and ask your question, Wing.
Hi.
Hi.
Hi, Professor Basri. My question was on more of the diversity side, where I was wondering, do you have any particular anecdotes or particular examples where certain faculties were either penalized or I think now the system does reward people for increasing diversity in the UC and the CSU system. But in the past, do you have particular examples where someone maybe was penalized for doing something about this?
Oh yeah, that was the general practice. I would say when the millennium started, people who spent time, like women would have 2 or 3 times as many graduate students because they were the only woman in the department, and a bunch of women wanted to work with them, and they'd spend all this time advising and so on. And then when promotion came up, be like, oh, you didn't write as many papers as Joe Blow over here, who only oversaw 1 student. And no account was taken of, oh, well, yeah, sure, you had 10 students, but, that doesn't really count. What counts is papers. So there was a lot of that, actually. There was a lot of that. And not much reward. I pushed that thing in the late 90s because I was doing, quite a bit of work. And it turned out there was a clause in our reward system that said, if the faculty has done exceptional work in one of the areas of merit, namely teaching, research, or service, they could get a half-step acceleration once, just for that. And I said, well, here's my list of things I've been doing in the service arena. I think that deserves a half-step acceleration. And they actually gave it to me. So then I thought, oh, well, this is good. We should make this a more constant practice. But yeah, now it's absolutely in the personnel manuals, and our faculty biobib has a place where you would write what you did in that arena. And like I said, people have actually come to feel, although it's not true, that they should all have something to say in that box. That was actually one of the big fights that we had when we were trying to put this in place. People said, well, I'll be penalized if I don't put something in the box. And I would argue, well, I said, well, we reward people who get Nobel Prizes too, but if you don't have one, we don't penalize you for that. We just reward you if you do it, and this is going to be the same thing. If you do this extra work, you should get extra credit. But if you don't do the work, no, we're not going to penalize you. We're just not going to give you extra credit. That fight came up again about 3 or 4 years ago. Some people in the academic senate said, hey, this isn't really fair. And we had to go through the arguments again. So, yeah.
Thank you.
Okay, and we have a 3rd question here. So let's go to Andrea and Tony. You can go ahead and ask your question.
Can you hear me?
Yes.
So I was just wondering, Gibor, if you have any suggestions for, let's say the graduate programs can be structured to reward the DEI work that students are doing. I mean, we have teaching requirements and we have course requirements, and, you know, we're doing research.
Right.
So of course at Berkeley, this is an active sort of issue that we're discussing. And I was just wondering if you had any thoughts on that.
Well, of course, the advancement criterion for graduate students is to get your degree. And that's maybe less subject to acceleration. What I would say is people should be supported if they're doing that work, and also not penalized for doing it so long as they're not impeding their own progress towards their degree. Funding, you know, funding for, like if a graduate student wants to start a program, they should do so, you know, advisedly, so it doesn't totally stop them from finishing their thesis. But then they could get support from, you know, from funding or from staff work or faculty or whomever to do that. And recognition is another thing that can happen. You know, we could have more awards for people who did good work, and recognition of that. You know, there is some reward for it because a lot of universities are moving towards asking folks what they've been doing in this arena. And so if you've been doing something amazing in this arena, that stands you in good stead on those applications. So I think it's those kinds of things that are probably where that could be done.
Great, thanks.
Okay, so let's all virtually thank Gibor again for, oh, well, okay, actually we have one more question that just came in. Well, we can do that before we wrap up. Okay. Eric, let me make that, Eric Sandquist, let me make that you can speak here and you can go ahead and ask your question. Go for it, Eric.
I was just curious if you could maybe share with students about what do you think helped you be successful in persisting in the field, and if you had particular obstacles that you encountered along the way?
Well, I think the thing that made me most successful was my passion for the work. You know, it's just always fun. You know, my main issues with my family, for example, is, you know, yeah, I really want to, you know, go hiking with you guys, but yeah, I really want to finish this code too. You know, it's like, so I think, you know, it's hard. Yeah, I mean, I know what you're asking. So you never know basically how your research career is going to go or where it's going to go or where your next idea is going to come from. I think you have to just let it flow. You know, it's an interesting topic. You get interested in something, and my experience has always been once that happens and you start digging into it, new questions start appearing, and some of them seem pretty interesting, and you know, you'll latch onto a couple and they'll take you in new directions. It just kind of went by itself. I did not encounter a lot of resistance to my success, and in fact, I would say, you know, for example, I got the Chancellor's postdoctoral fellowship. That was the first year that was there. That was an affirmative action thing. You know, I took great pleasure as Vice Chancellor in running that program much later. So that was helpful. It wasn't an impediment. The impediments were partly psychological. You know, I mean, we all have imposter syndrome and stereotype threat and various things. And, you know, I had to deal with those in my own head and with help by talking to other people and you know, getting good networks of peers and supportive scholars and so on that's the way to make that happen and not get in your way. Direct racism, I experienced it outside academia enough, but not inside. You know, my department hired me. They wanted me to succeed. So yeah, I don't know if that answers your question, but a lot of that stuff ends up being sort of internal and psychological. If there is direct racism, then you got to figure out who is going to get on your side to deal with it. You know, as vice chancellor, I had to intervene. This happened more in the social sciences and humanities than it did in the sciences, I would say. Partly because, of course, there were very few of us in the sciences, but there we had direct knockdown, dragouts, you know, they didn't look like racism, but they kind of were, because people didn't like the topic that other people were working on, or they didn't like the way they were working on it. And they weren't willing to sort of open their mind to the idea that, yeah, actually, if this Latino sociologist wants to study day workers this way, he probably has a much better idea how to go about it than you do. But, you know, then they would write, you know, crummy reviews, and then we'd have to deal with that. So it was more like that that I saw, but personally, I didn't experience it that much.
Okay, so we'll wrap up things with our questions at this point. So I'll virtually thank Professor Basri, sorry, for a nice talk. One thing that I forgot to say earlier, so we're going to have an informal discussion now with Professor Basri, and I'm putting into the chat here a link for that. The CalBridge scholars are particularly invited to take part in that, and this is something we'll be doing after all of the talks in the series, so you have a chance to chat with the different speakers who we have. Yeah, and the other thing is that this seminar series is being sponsored by the Research Corporation for Science Advancements, so thanks to them for that. And then finally, yeah, I think Alex, did you want to say something?
Oh, no.
Oh, no.
Sorry, I was going to ask a question, but then I realized we're over time and I want to leave time for Gibor to talk to the students. So it's fine.
All right, fair enough. Okay, so yeah, with that, thanks everybody for attending. Please join us for the future talks. Check on the website all of the great speakers we're going to have this semester. And right after this, I'll fire up the Zoom session for the discussions with students in Gibor. And thanks everyone for attending.